Hi everyone, I wanted to make a video today about everything that you need to memorise for your pure maths A-level exam. I've got here a copy of the formula book. I don't let my students use this unless we're doing a timed exam during class or for the real thing. And there's 3 reasons why I want you to memorise stuff, even if it's inside this formula book. First of all, it's to save time. Flicking through here and looking for something that you think might be in there can actually be quite a waste of time. The second thing is when you're trying to look for something and you're flicking through, I've seen students doing that and it looks like quite a stressful experience, and I want you to be able to avoid that feeling. That kind of links into the second reason of reducing stress, but also increasing your confidence. If you've got these formulae memorized, you just feel like really pro at what you're doing, and that can make you feel good in the exam, which is something that you shouldn't underestimate. The third reason is that if you have these facts memorized, you can often solve problems way more efficiently. And I'm thinking in particular of integration. If you know lots of the standard results off the top of your head, you won't be trying to think of a trig identity. You'll actually just know what it is that you're looking for. There are a few things that I will have noted on the document I'm writing that are in the formula book, and I've put a little blue F next to those. And there are some of them where I've put a little heart next to that blue F, which means that I think you should learn that off by heart, even though it's in the formula book. To learn by heart actually means to have a good understanding of what it's talking about and then to memorize that fact. I will also make a copy of this that you can download from the description, which is going to be a PDF. I'm going to do one version that's got blank parts for you to fill in, and I'll do another version which is my completed copy of this. So we're going to get started, and I'm going to talk you through some of my tips of how I remember everything on this page. Okay, so here it is, everything I think you need to know for your pure maths A-level. There's quite a lot of information on here. I'm going to take you through column by column and tell you some of my tips of how I remember these things. Okay, so let's get started. Up in the top corner, I'm just going to remind you of what I said was about the key. So I've said, if I've written a little blue F next to it, it means that it is in the formula book. If there's a little blue F with a red heart, that means it's in the formula book, but I recommend learning it by heart. Okay, let's try and do the whole of this page in one take. So to start with, we've got the algebraic laws, the index laws. When you're multiplying them with the same base, you add the powers, so you get a to the power of n plus m. When you're dividing them with the same base, you get a to the power of n minus m, you subtract them. Brackets means you multiply the powers. To the minus power means you take the reciprocal and keep the same power there, but no longer negate the power. If you have something to 1 over n, you will take the nth root of that particular base. And anything to the power of 0 is 1. The next thing is the log laws. Log base a, n, equals x is the same thing as saying that a to the power of x is equal to n, because I'm saying here that the base is a, the power is x, and the answer is n. Log of xy, or I say ln xy, is ln x plus ln y. Log of x over y is ln x minus ln y. And this one you can bring the power down, so ln of x to the power of k is k ln x, and ln 1 over x is minus ln x. Ln e is 1, and ln of 1 is 0. So they all also work with logs of any base. I just like writing them with the natural logarithm. So the factor theorem, if f of a is equal to 0, then x minus a is a factor of f of x, and vice versa, meaning that applies both way rounds. Then looking at inequalities, negating flips this symbol to this symbol and vice versa. So if you ever negate an inequality, you've got to make sure you flip them over. With partial fractions here, I've got a repeated linear root. This is a special case. This would go to a over x plus a. You'd also have to have a b over x plus a all squared, and you also need to have the x plus b part as well. So this is the extra part that you need to remember for these 2 bits. Okay, we're going to now move on to geometry. So these ones are back from GCSE, so they should be pretty easy for you to remember. The cosine rule is that a squared equals b squared plus c squared, which is Pythagoras, and then you minus 2bc cos a. The sine rule is that sine a over a equals sine b over b, which is equal to sine c over c, and you can have this same formula where everything is flipped over. the area of a triangle is just a half AB sine C. And I've got this triangle at the top here, which allows you to remember the orientation of the sides and the angles. I've written here GCSE circle theorems. I'm not going to take you through all of them, but you need to make sure that you know all of the GCSE circle theorems. So for these ones that I've got a reminder of what the triangle, sorry, not the triangle, what the sector looks like. I'll zoom out a little bit so you can see that the whole time. These all must be in radians. The arc length is r theta, the sector area is a half r squared theta, and the segment area, which is this little top section that I've got here, is a half r squared theta minus sine theta. And I've just done a reminder, the arc length is this bit, the segment is this section, and the sector is the whole piece of pizza slice, as I call it, together. Okay, let's go now on to the next part, which is to do with functions. So just as a reminder of like the definition of functions, if you have a one-to-many function, it is not a function. So one-to-many, not a function. It's good for a one marker. So the domain is the input, which is obviously the x values. The range is the output, which is the y values. For composite functions, if we have something which is g, then f, you actually write it the other way around. So this is saying you do g, and then afterwards you do f. For inverse functions, we know that, what was I going to say for inverse functions for this part? Yep, the domain and the range switch places. We reflect it in the line y equals x. And also to be able to find an inverse function, you switch x and y, and then you rearrange. That's how you actually find an inverse function. Now we're going to move on to graphs and coordinates. Some of these are pretty straightforward. So for a midpoint, you know that you do x1 plus x2 over 2, you take the average, and for the y coordinates, you also take the average. The gradient, m, is the change in y divided by the change in x, which you may see in a different form, but I like using the delta triangle there to show that there is a change. For perpendicular gradients, if m1 and m2 are perpendicular, then m1 is the negative reciprocal of m2 and vice versa, or you could say that m1, m2, when you multiply them, is equal to -1. Either of those work. Now the discriminant, the equation of a line, it is y minus y1 equals m brackets x minus x1. If anybody uses y equals mx plus c, I highly think you should not be doing that at all. I do not recommend that at all. For the discriminant, well, the discriminant, you first of all need to memorize that it is b squared minus 4ac, and we need to think about the three different conditions that we've got here. If it is greater than 0, then there are 2 roots. If it is equal to 0, then there is 1 repeated root, and if it is less than 0, then there are no real roots. Now I'm going to think about drawing the reciprocal graphs. So if you have k over x, where k is a positive number, you have a graph that looks like this. If you have y equals minus k over x, then you have a graph that looks like this, and this is obviously for k being a positive number. If you have y equals k over x squared, you have these kind of, both of the bits coming upwards. I kind of say they're like praying hands. And if you have minus k over x squared, you have the same kind of thing, but it's coming downwards like this. Having a look at circles, we know that the equation for the circle is going to be x minus a squared plus y minus b squared equals r squared. And that is for a circle that has the center AB and it has the radius r. I've just got 3 graphs, the sine, cosine, and tan graph here. You need to know their shapes. You need to know all of the key values for these parts as well. I'm not going to talk you through that in much detail. All I remember is just that the sine starts at the origin and cos starts at 1, and they all vary between 1 and -1. Sorry, sine and cosine vary between 1 and -1. Tan actually can take any value at all. Having a look at the transformations now, transforming f of x. If you do f of x plus a, that is just going to shift it upwards, a vector 0a. If you do f of x plus a inside the brackets, it actually goes to the left, so it would be minus a 0. This one is a stretching in the y direction, a scale factor of a. This one is a stretching in the x direction and a scale factor of 1 over a. This one is a flipping, and it flips over the flips over the x-axis, but really it's a vertical flipping. So I like to think of this as like flipping, but it's also a reflection. And this one here is a flipping left and right, or a reflection, but this time it's a reflection in the y-axis. And I'll tell you about why I call it flipping in just a second. So when you do the modulus on all of the outside, anything below the x-axis goes up. And in this one, anything to the right of the y-axis goes left. And so there's some ways I like to remember this. Everything here, all of the changes are outside the f of x. And so they do the kinds of things that you expect, and they also move in the up and down direction. So this is a translation upwards, this is a stretching up and down, this is a vertical flipping, even though it's a reflection in a horizontal axis, the flipping itself is vertical. And again, you've got something from up and down, something below moving up. These ones are all inside the brackets, and so these affect things to do with the x coordinates, and they also do kind of the inverse or the opposite of what you might expect. So this one, instead of moving a to the right, it moves a to the left, and the scale factor here is the reciprocal of what you might expect it to be. This one does what you'd expect, and this one also similar to kind of what you would expect. So I think those are definitely worth memorizing. Okay, we're now going to move on to vectors. So for position vectors that we've got here, AB is going to be equal to B minus A, and it's always the second letter minus the first letter that we've got here. The parallel condition, A and B are parallel if A is equal to lambda B, where lambda is a constant. The magnitude, if A is equal to xi plus yj plus zk, then the magnitude of A is just going to be x squared plus y squared plus z squared. It's basically just Pythagoras to those values. And a unit vector is 1 divided by the magnitude multiplied by the vector itself. The angles with axes that you've got here, so the angle with the x-axis, which is denoted by this, is just x divided by the magnitude of the vector. With the y-axis is the y-coordinate divided by the magnitude of the vector, and with the z-axis is the z-coordinate divided by the magnitude of the vector. So now we're coming to our first one that actually appears in the formula book. So it's not necessarily one I recommend memorizing, but I like to have it on this page because I actually do like to memorize this as well, personally. So the binomial coefficient, n choose r, or nr in those brackets, is n factorial over r factorial, n minus r factorial. And the formula, although it is in the booklet, this is for your 1 plus x to the power of n, is 1 plus nx plus n minus 1 over 2 factorial x squared plus n minus 1, n minus 2 over 3 factorial x cubed. And you can just see how that pattern would continue, that you'd then have n minus 1, n minus 2, n minus 3 over 4 factorial x to the power of 4. And this bit's in the formula book that it only works for when the modulus of x is less than 1. The other form is something that I think is worth memorizing, that if you would actually need to factorize out the a, because the formula only works when there's a 1 to start with. So if you factorize out the a, you would have a to the power of n, 1 plus bx over a to the power of n, and then you would apply the formula as before, but this is only going to apply for bx over a being less than 1, for this second part being equal to 1. This thing here is what people usually forget. They forget to raise the power, they forget to raise the thing they factorize by that power. Okay, we're going to have a look at series. So the arithmetic nth term does not appear in the formula book, so you are going to need to know this one, and it is a plus n minus 1d. Now this one is actually in the formula book, but I think it's worth having at your fingertips. It is n over 2 brackets 2a plus n minus 1d. And the second one here is n over 2 brackets a plus l, where a is the first term and l is the last term. the geometric nth term, not in the formula book. It is AR to the n minus 1. The geometric series and the sums of those series, you have a brackets 1 minus r to the n all over 1 minus r, and the sum to infinity is a over 1 minus r. These things people forget about. They're often good for like a 1 marker. It says it's an increasing sequence if u of n plus 1 is greater than u of n for all n. It's a decreasing sequence if it's less than u of n for all n. And it's a periodic sequence, it should say. A periodic sequence if n plus k is equal to un for all n. And its period or order is k. So a periodic sequence is a repeating sequence that we have here. Okay, let's have a look now at probably one of the biggest areas, and I really think there's a lot to memorize here, is trigonometry. So first of all, it's your conversions between degrees and radians. You should know most of these already. 2 pi is 360 degrees, pi is 180 degrees, pi over 2 is 90 degrees, pi over 3 is 60 degrees, pi over 4 is 45 degrees, and pi over 6 is 30 degrees. Really, most of the ways I remember this is by looking at the 180 degrees and thinking about all of the different relationships with the fractions of pi. Now, the small angle approximations are in the formula book, not necessarily something that I think you do need to memorize, but I do know them. Sine theta is approximately equal to theta, cos theta is 1 minus theta squared over 2, or half theta squared, and tan theta is approximately equal to theta. The exact trig values, the amount of times I tell my students to learn these and I don't think they actually do, really frustrates me. You should know these. Sine 30 is the one I really start off by memorizing. Sine 30 is a half, which means that cos 30 can't be a half, so it's therefore root 3 over 2. Well, if cos 30 is root 3 over 2, then cos 60 has got to be a half, and that means that sine 60 has got to be root 3 over 2. I also know that sine 45 and cos 45 are both equal to each other, and they are both 1 over root 2. You can memorize them in their rationalized form of root 2 over 2. Personally, I prefer memorizing them in the 1 over root 2 form. Tan 30 and tan 60, well, I think here that because the angle 30 is smaller than 60, I know that the result of tan 30 is smaller. It's 1 over root 3, and then tan 60 is root 3. I remember that because the smaller angle has the smaller result, and the bigger angle has the bigger result. Last of all, tan of 45 is 1, and you would need to know all of these in their radian form as well. The definition of tan theta is sine theta over cos theta. And when you solve equations, if you have sine theta equals something, sine theta is equivalent to sine of 180 minus theta. So you can get your answer and just do 180 minus that answer. And of course, you can plus or minus 360 degrees to those as well. For cos theta, it's 360 minus theta. And again, you can plus or minus 360 degrees. And for tan theta, all you need to do is plus or minus 180 degrees to your answers. The reciprocal trig functions now. The way I remember the reciprocal trig functions is the third letter gives you the clue. So cosec theta is 1 over sine theta because of that s linking. And 1 over cosec theta is obviously then going to be sine theta. So sec theta, the third letter is c, so it's the same as 1 over cos theta, and 1 over sec theta is therefore cos theta. Cot theta is 1 over tan theta, but it's also worth knowing that 1 over tan theta is the reciprocal of tan theta, so it is cos theta over sine theta. The cofunction is one that people often don't memorize. So sine theta is the same as the cos of 90 minus theta, and likewise cos theta is the sine of 90 minus theta. It's called the cofunction because it's sine and cosine. It's also true for sec and cosec, and it's also true for tan and cotan, which is cot. The Pythagorean identities. Everybody remembers sine squared theta plus cos squared theta equals 1, and it actually comes from a right angled triangle. But these ones you definitely need to memorize. It is 1 plus tan squared equals sec squared theta. And I want you to remember that tan and sec appear together here because they appear together later on as well. The last one that we have of the Pythagoreans is 1 plus cot squared theta, which is equal to cosec squared theta. Again, I want you to remember that cot squared and cosec squared, or cot and cosec, appear together here because they do appear together later on. They're not related to the identities I have later, but they just happen to pop up together, so it's worth remembering those. The addition formulae, okay, these are in the formula book, but I strongly recommend having these ones by heart because it's some simple patterns. So for sine of a plus b, you start off with sine a cos b. So you have a different function for sine and cos, and then you do get the same plus minus, and then you flip this, so you have cos a sine b for the next part. The difference with cos a plus or minus b, instead of it being a plus or minus in the middle, it's a minus plus, but instead of it then being a mix of sine and cos, it actually just starts the same. It's going to be cos a cos b, and it's going to be sine a sine b. It's also worth noting that for cos, it starts with cos. For tan, you get tan a plus tan b, plus or minus tan b, all divided by 1 minus plus tan a tan b. The double angle formulae are variations of the addition formulae, and if you know the addition formula off by heart, you should understand the double angle formulae. So sine 2 theta is 2 sine theta cos theta, and cos 2 theta has 3 forms that you need to memorize all of them for. So cos 2 theta is cos squared theta minus sine squared theta, but you can also then use the Pythagorean identity to come up with the fact that you have 2 cos squared theta minus 1, and you also have 1 minus 2 sine squared theta. The way I remember this is that the cos ones always lead first, which then means that the sine squared bit can't lead first. Tan 2 theta is 2 tan theta all over 1 minus tan squared theta. Now I've got here the rearranged double angle formulae. These are one of my top ones to memorize, especially if you're doing further maths, because these are used a lot in integration. If you had to integrate sine squared theta, you have to use a rearranged version of this one that we've got here. And the rearranged version of this is a half minus a half cos 2 theta. Again, if you wanted to integrate cos squared theta, you would need to rewrite it in the rearranged double angle formula, and it's a half plus a half cos 2 theta. Memorize these. They are a big time saver for integration. Last of all, for trigonometry, we've got the harmonic identity, which is actually this thing. Most of you will see it in that form. I call it the harmonic identity. So if r cos alpha is a and r sine alpha is b, then r is just Pythagoras of a and b, and tan alpha is sine over cos. So you have b over a. Okay, we're doing pretty well. Let's zoom out and see how much we've done so far. We've done most of it. We've just got the big ones, differentiation and integration. So for differentiation that we've got here from first principles, this is in the formula book, so you may not want to memorize all of this here, but it's the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. First derivatives, people always forget about these ones that we've got here. If f dash x is less than 0, we say that it is a decreasing function. If it is equal to 0, we would say that the point is stationary. If it's greater than 0, we would say that this is an increasing function. For the second derivatives that we've got here, if the second derivative is less than 0, we would say that the function is concave, or it also corresponds to a maximum value. If it's equal to 0, it corresponds to a point of inflection. If it is greater than or equal to 0, or just greater than 0, we would say that it is convex or that it is a minimum. There's a bit of disagreement. The textbook sometimes includes these lines, it sometimes doesn't. I can let you know now, the mark scheme will let you have it with or without that extra line, it doesn't matter. Functions and their derivatives. Okay, this is a big one. So we've got ax to the n will differentiate to anx to the power of n minus 1. So you pull the power down and reduce the power by 1. A to the power of x goes to ln a multiplied by a to the power of x. E to the x differentiates to e to the x. Ln x to 1 over x. Sine goes to cos, cos goes to minus sine. These four here are all in the formula book, but I think you need these in your memory. Tan goes to sec squared x. Sec goes to sec x tan x. And now for cot x, because cot is related to tan, it's going to be the co-version of that one. So it'll be cosec squared x, and it is negated. Cosec is related to sec, so it's going to be the same as this one, but with cos. So it'll be cosec x cot x, and it's also negated as well. The chain rule. If you've seen any of my videos on differentiation, you'll know I call the inside function blah. So what you would do if you had f of blah, you would differentiate that function as you would expect to get f dash blah, and you would also multiply it by the derivative of blah. Not super formal notation, but it's how I like to remember it. If you have the function uv, you use the product rule. So you do u multiplied by v dash plus u dash multiplied by v. When you write them out and you differentiate them to go from u to u dash and v to v dash, you do these two multiplied and these two multiplied. That cross symbol that we've got there is like a multiplication symbol. So that's how I remember it with the product rule. The quotient rule is v u dash minus u v dash over v squared. I remember this one in one way of it looks like vuv over v squared. The other way is I do v u dash minus u v dash, and it kind of looks like the Greek alpha letter that we use. Implicit differentiation, if you have f of y and you're differentiating it with respect to x, you differentiate it with respect to y as you'd expect it to do, and then you multiply by dy by dx afterwards. The quotient rule is in the formula book, but it's not in a very simple form. I prefer this one, so it's better to try and memorize that. Okay, nearly there. Reciprocals now. dy by dx is the same as 1 over dx by dy and vice versa. For parametric ones, you just do dy by dt divided by dx by dt. For connected rates of change, if you have something like dv dt, for example, you split it into these two and you think what needs to go in these places here to be able to connect those rates of change together. Rate, if you see that word, means dt, something over dt. Coming on to numerical methods now. So talking about roots, if there is a change in sign and if the function is continuous over the interval, that shows there's a root. If you don't say it's continuous over the interval, you lose the mark. Having a look at staircase and cobweb diagrams that we've got here. So I've got a few different examples we're going to do. To start off with though, you need to know that you begin with the iterative formula. That's where you start drawing towards, and then you draw to the line y equals x, and you keep doing that pattern. So for this first diagram that I've got here, I'm going to go from this starting point. You're going to go up to the iterative formula curve, then you're going to go across to y equals x, and you're going to keep doing that pattern. You can see that this one here, it converges, and it's also an example of a staircase diagram. This one, I'm going to go to the iterative function, then I'm going to go across to y equals x, then iterative, y equals x, iterative, y equals x, iterative, y equals x, and you can see again that this one is converging to a value, but this one is a cobweb diagram. Last one that I've got here, I've got y equals x and the iterative formula. I'm going to go up to the iterative formula, then across to y equals x, up to the iterative formula, and you can see that this one here is not going to converge. In fact, it is going to diverge, but it is still an example of a staircase diagram that you've got here. You can also have a diverging cobweb as well. So the Newton-Raphson method is actually in the formula book. It's not necessarily one that I think you should memorize, but it's xn minus f of xn over f dash of xn. And I'm just going to check I've got that one right because it's in the formula book. Yep, that's good. And it fails if the denominator is equal to 0. So it's worth knowing when the Newton-Raphson method fails. Okay, let's just quickly see how we're doing so far. We've got most of the stuff done. We're just going to have now a look at integration. So here we're going to just have all of the integrals. You'll notice that they all should have plus c at the end, so I'm not going to be writing plus c each time here, okay? Zoom in a bit so we don't get confused with all the other stuff on the other side of the page. So for this one, you have ax to the n. We know that we increase the power by 1 and we divide by that new power. E to the x integrates to e to the x. 1 over x integrates to ln x. You need those modular signs. It's to do with keeping it positive. So cos x integrates to sine x. I kind of remember this just because sine differentiates to cos. So the integral of sine x is minus cos x. The integral of sec squared x is in the formula book, but I think you need to know this one because we know that tan differentiates to sec squared, so the integral of sec squared is tan x. The integral of sec x tan x is sec x, not in the formula book. The integral of cosec squared x is going to be, well, it's related to this one that we've got here. It's like sec squared and cosec squared, so it's going to go to cot x, but it's going to be negated as it was before. This one is going to go to cosec x because it's similar to the sec x one, but it's also going to be negated as before with differentiation. If you have a function that looks like the derivative of another function, we know we can integrate it to that function, but because of the coefficient of a here, we're going to have 1 over a to scale it correctly. Plus, there are more in the formula book for things like how do you integrate tan x, how do you integrate other trig functions, and it's worth having a look in the formula book for those ones, but they're quite rare. The reverse chain rule. For the reverse chain rule, if you've watched my videos on this, you need to consider what function that you think it should be, and then you need to scale that function so that it works correctly for you. So for substitution, I like to remember this little phrase here. I've got Sir loves derivatives. So there are three things you need to do for a substitution. One of them is the actual substitution itself. The L stands for the limits. You need to change the limits so that they match what you're integrating it with respect to. And obviously the derivatives part is just to correspond to the fact you need to do the derivative of u at some point to be able to do that full transformation. Integration by parts now. This one is in the formula book, but I highly recommend knowing this because it can speed up a quite stressful kind of question. This is that the integral of u v dash with respect to x is equal to uv minus the integral of u dash v. And when I think of this little diagram that I've got here, I've got the red line here, which is representing the thing you're integrating, which is uv dash. The answer is then uv minus the other pair that you haven't yet integrated. And I should have put here that this is with respect to x. You also should know that ln x takes priority for u, and you need to use integration by parts if you want to integrate ln x. Parametric integration, you integrate y dx dt, and you need to make sure that you change the limits, because the limits always need to match the thing that you're integrating with respect to. So some general tips for integration here. I've said my little phrase is Sir really adores partial fractions. So the S part that we've got here is a recommendation that you can split the numerator. You cannot split the denominator, but you can split the numerator, as in this example that we've got here. That can then make things easier to integrate. The R part for Sir really adores partial fractions is the reverse chain rule. I would say that most integration questions can be done using the reverse chain rule. I'd say anything as close to 50 or 60% of questions are the reverse chain rule, and people make them way too complicated. The A here stands for algebraic division. It's not always got to be done, but often algebraic division can make things that look like this become way more simple to integrate. And then obviously the partial fractions part stands for the fact that you can do partial fractions if possible, and that will take a couple of things like this and will make them a lot easier to integrate. I think we're on the very last bit now. This one is in the formula book. So the integral of y with respect to x, the trapezium rule, is a half h brackets, first plus last. It's not like this in the formula book, but this is how I remember it, plus two lots of the middle values. And these are the y values that we're talking about here. So this is by some maths. This is everything that I think you need to memorize for your pure maths A-level. I will give you some blank versions of this. Hopefully you can get this committed to memory. Well done for making it to the end of that video. There's an awful lot of stuff that you need to memorize. Really though, if you just do a lot of practice, most of those formulae should be going into your head. I think you should be trying to ditch this as much as possible. It will save time, make you feel less stressed and more confident, and it's also going to be able to help you to solve problems that at first you might be confused of what you need to do. Hopefully you found that useful. I'm going to be doing some more videos like this for mechanics, statistics, and for further maths as well. So if you liked the video, consider subscribing to my channel. If you go to my channel homepage, you'll see I've got hundreds of videos of my real lessons with students in school, all linked to the Edexcel Pearson textbook. So if there's something you're not so sure about and you want to do some revision, you can go and see each chapter in nicely organized playlists to help you out. Good luck with all your revision, and I hope that things go well for you.